statistical topic. Of course, we started probability distribution of a discrete random variable. Um, I've walked you through different kind of probability distributions of discrete random variable. We talk about Bernoulli, binomial, geometric, negative binomial, and of course, we're going to talk about Brown-New probability distribution for discrete type. Today, we're going to be talking about Poisson distribution and discrete uniform as well. But you know what? I make sure in today's lecture, I'm also going to have a recap on the probability distribution for discrete random variable we've been doing. So that's why I have this outline. Okay, let me quickly, because what I'm going to do today, I'll four of us show, walk you through some uh, provision I have in the slide before making use of the board, because we're going to be making use of the board more often, because we've entered into a stage where you need extensive explanation, step by step. So this is geometric distribution. Of course, yesterday I derived what the mean, the variance, and of course the standard deviation. I walk you through examples. Okay, and now how are you going to know if you are working with geometric distribution? You actually need to pay attention to a particular word that will be mentioned, like the probability of the first, you know, stuff like that. So now I actually walk you through all these examples yesterday on geometrical distribution. Now, going to the negative binomial distribution, like I said, the binomial distribution is a generalization of geometric distribution. Instead of us to talk about first sources, we're actually going to talk about high root sources. So which means we're not seeing sources for the first time. So what I'm showing you now is the probability mass function for negative binomial distribution. Now, this is the mean. Expected value of S is this. The variance of S is this. And of course, the probability generated function for that. So I think I'm actually going to walk you through some of that. Now, this is an example under negative binomial. I think I showed you yesterday. So you have to be given P, you have to be given R for you to be able to, figure out a problem associated with negative binomial. And of course, what is going to be new that I'm also going to walk you through today is what we call the discrete uniform distribution. What is the essence of discrete uniform distribution in real life? I think I'm going to walk you through all of that. But this is what I know. Whenever you are dealing with any probability distribution, there's always going to be mean and variance. We're going to have an expression for mean and variance. And of course, you can be asked to derive the mean and variance of any given probability distribution of a random variable, whether discrete, whether continuous. I'm also going to show you how this is being derived today. How do we know that if we have a probability mass function of 1 over n, where s starts from 1 to n, how can we derive that the mean is n over 2, n plus 1 over 2? And how do we derive the variance to be 1 over 12 n squared minus 1? I'll show you all of that today. Now, the next distribution is Poisson distribution. It's another probability distribution of a discrete random variable. And of course, I'm going to tell you the significance of this distribution in real life when I'm, writing something on the board. Like what I'm trying to do right now is just to quickly walk you through this on the slide before doing extensive derivation on the board. So we have Poisson distribution. It's a distribution of a discrete random variable. We use this distribution to model rare events, like events that occur in a blue moon, events that don't just occur frequently. Okay, so we use that, and we have a probability distribution. It stands for formula for Poisson, okay, which is what you are seeing right now. The probability mass function of Poisson is that. Then we can also derive the mean, the variance, and the standard deviation, of this distribution as well. Okay. Now, I think I provided some examples on Poisson distribution here. Okay, the calculative examples. Okay. Now, I'm actually going to walk you through all of this. Of course, what I have for you tomorrow is hypergeometric distribution. The hypergeometric distribution will be the last probability distribution for discrete family that we're going to do. Okay, now let's get started. Now, I need you to pay attention. I'm going to be doing a lot of stuff on the board. Okay, because of that, I actually need you to pay attention. Now, I'll start my review because these distributions actually, they are connected. Okay, and I need you to pay attention. We started all the way from Bernoulli. Okay, we are, this week the focus is actually has been on probability distribution of a discrete random variable. There are so many of them. I started with Bernoulli. And mathematically speaking, if you see stuff like this, okay, we're trying to say a random variable x follow Bernoulli distribution with parameter p. So that's random variable x. So it's actually going to be p raised to power x, q raised to power 1 minus x. S start from 0 to 1. Now, what do we use Bernoulli distribution to do? We use Bernoulli distribution to model a single trial with two possible outcomes. That's why here x is a number of success. Okay, if I try once, here we are trying the numbers of trials is actually 1, and we said that we see 0 success of 1. And of course, I remember I derived the mean expectation of S to be P, the variance of S to be PQ. And of course, the standard deviation of S is going to be square root of PQ. Don't also forget Q is 1 minus P. Okay, now this is Bernoulli distribution. Now, based on the assignment, I actually uploaded assignment yesterday. Do you know you can also do some linear combination with Bernoulli? Okay, for instance, if a question is actually read, okay, please pay attention. If a question is actually read this, okay, and somebody said, and y is 3x minus 2, for instance, and somebody can say, find the expected value of y, find the expectation of y squared, find the variance of y, find the variance of y squared. How do I solve a problem like this? If you don't understand, you need to ask me question, okay? If you don't understand, you need to ask me a question, okay? Now, how do I, you know that this is Bernoulli, the mean, the variance, the probability distribution. Now, you were actually given that, okay? You actually giving like I said, Bernoulli with Bernoulli P, and y equal 3x minus 2. And somebody said, what is the expected value of y? What is the expected value of y squared? What is the variance of y? And what is the variance of y squared? Now, if I want to find the expected value of y now, okay, expected value of y will be expectation into 3x minus 2. Okay, if I have expectation into 3x minus 2, so this is going to be 3 expectation of x minus 2. And of course, when x follow Bernoulli, that implies expectation of s equal to p, the variance of s equal to p cubed. Okay, if x follow, you have to know that from the theory. When x follow, I think I also remember expectation of x squared is also p. Okay, so since they've told you that it follow Bernoulli, okay, you need to be able to recall what is the expectation of x, what is the so right now I'm going to plug in expectation for x. The expectation for x is p. So here I'm actually going to have 3p minus 2. I'm done. So which means expectation of y is 3p minus 2. So whatever they give us for p, okay, you're actually going to plug that in. And if you're not giving any value for p, then your answer is going to be in terms of p. Does that make sense? Now, that is how, so the same way if I want to do expectation of y squared, if I want to do expectation of y squared, okay, so expectation of y squared, then I'm actually going to know that I need to do 3x minus 2 squared, okay? I have to do this guy squared. You have to expand this one first. So expectation into, so that's going to be 9s squared plus 12x, okay, plus 12x plus 4. Who doesn't know how to do this? This is math, 3x minus 2 all squared. And of course, if you come right here now, okay, right here now, let me write up here so that you can see. Okay, so if you come right here now, this is going to be, so the expectation of y squared is going to be 9 expectation of s squared minus 12 expectation of s plus 4. Isn't it? And of course, 9, what is expected value of s squared for Bernoulli is p. Is p. This is also p. Then plus 4. Look at that. So what is 9p? So this is going to be negative 3p plus 4. So this is expectation of y squared. So take a look at that. Now you can figure out the variance of y squared. Let me just write that somewhere, the formula. If you want to figure out the variance, if you want to figure out the variance of y, of course, the variance of y. Okay, so the variance of y is expectation of y squared minus expectation of y all squared. Okay, so if you get expectation of y, okay, expectation of y, which is what you get here, you square it. Then expectation of y squared, then you need to, the one you got here, then you now use the formula, you get the variance of y. If I want to get the variance of y squared, okay, the variance of y squared, okay, we actually mean, okay, now if I were you, if you want to get the variance of y squared, why can't you do this? If you let, if z equal y squared, what is going to happen? This is going to be the variance of z, right? Variance of y squared if z equal to that, and what that is going to be expectation of z squared minus expectation of z all squared, right? So if I want to rewrite that, okay, z squared, don't forget, that would be y4 minus expectation, okay, y squared, this is going to be all squared. Look at that. So for Bernoulli, what is the expected value of y4? Can someone tell me? For Bernoulli, what is the expected value of y4? Want to tell me? What is the expected value of y4, y to the power of 4 for Bernoulli? is P. Expected value of y is P. Expected value of y squared is P. Expected value of y raised to the power 3 is P. Expected value of y raised to the power whatever is P for Bernoulli. So this is going to be P. Okay? And if this guy is P, what is the expected value of y squared P? So that will be P squared, then you get your result. Okay, so that is for Bernoulli. Now, the next that I want to talk about, now you understand what Bernoulli means. We got a single trial, okay, with two possible outcomes. Now you should be able to know how to derive the mean, how to derive the variance, and how to solve a problem that has to do with linear combination. Okay, I want to go to binomial. I want to go to binomial now. Now, in going to binomial, binomial is a generalization of Bernoulli. Okay, binomial is a generalization of Bernoulli. Okay, now, okay, that's okay. Okay, so let me see this. Okay, so now if I have x followed by num with n and p, I want to talk about binomial now. Okay, now the probability of s is n combination s, p raised to the power s, q raised to the power n minus s, and the state space is 0, 1, 2, until you get to n. So binomial is a generalization of Bernoulli. In the case of binomial, we have more than one trials, okay, and x represent the number of success. Okay, P is the probability of success, Q is the probability of failure, and these are the state space for a number of success. I could have 0, 1, 2, or up to n, don't forget, or have n time, and there are two possible outcomes as well. So expectation of x is NP. The variance of s is NPQ. And don't forget, the sum of Bernoulli will give us binomial. The sum, if I want to derive this and that, remember the other time, we derive this and that from, having, from the idea of Bernoulli. So this is the mean, this is the variance. Of course, the standard deviation is going to be the square root of this guy. And don't also forget that, Q is 1 minus P. So you can see this formula, you can see that formula as that as well. So let me say this. If I'm testing patients, whether they have disease or not, if I only focus on one patient, okay, that will be Bernoulli. But if I have so many patients, okay, and I want to figure out what would be the what would be the number of patients that we have the disease, then I'm talking about binomial. Because the patient is more than one. I have so many patients, and I want to figure out, okay, or in a manufacturing company, we are, in every manufacturing company, they have internal quality control units, right? And before they send product to customers, they want to make sure whatever they produce conform to standard. Okay, so Bernoulli, we mean if you only investigate one item. If I investigate one item for defective, it could be defective or not, because it's one item that is Bernoulli. But for so many items investigated for defective, we want to figure out if I investigate 20 items, how many defective am I going to get? That will be binomial. Does that make sense? So if I now want to say, okay, on average, what will be the number of defective? Then I need the mean, expected value of S. Then what will be the variance? Then it's this guy. Any question on binomial before I move? Okay, now I'm going to move right now to geometric. I'm going to move to geometric now. Okay. Statistics is like a story. Okay. Make sure you understand what is behind the scene. Okay. Of all the formula. Okay. For geometric, when you say this, X follow geo with parameter P. Okay, S follow geo with parameter P, then we're referring to geometric. So the probability of X, okay, in geometry is this: Q, X minus 1, S start from 1, 2 to infinity. Now, in geometric, the geometric is trying to say, uh, you know, we want to figure out the numbers of Bernoulli trials before recording first sources. The numbers of, okay, for instance, we've been examining some products, we've been for quality, how many products are we actually going to investigate before we actually run into the one that is defective, the first defective. That would be this guy. And of course, hex here does not represent the number of sources because in binary and binomial, x represent the number of sources. But right now here, x in geometric represent the numbers of Bernoulli trials. The numbers of Bernoulli trial before recording the first sources. So in that case, the expectation of x is actually 1 over p. Okay, the variance of s is q over p squared. So when we talk about geometric, we're also going to figure out an average. Okay, we can derive an average from there. I think I showed you how to do that yesterday. We can also derive the variance for that. Now, from here now, we move to negative binomial. Now, the negative binomial is actually, a generalization of this guy. That is, how many Bernoulli trials am I going to have before recording a good number of successes? I'm not seeing success for the first time, but here they are seeing success for the first time. Does that make sense? So now, how do we write negative binomial? Okay, negative binomial. Okay, in the negative binomial, we're going to write x follow negative and b with parameter Rp. Okay, the parameter Rp. P is the probability of success, and R is the R success. So now the probability of S equal to this is going to be this. That's P raised to power R, Q raised to power N minus L, of Q raised to power X minus R, and S star from R plus 1, and so on like that. Now I need you to pay attention. This is a probability mass function for negative binomial. Now, there's something I needed to do right now. If R equal to 1, for instance, if you plug in R to be 1, you're going to come back to this. And that's why negative binomial is a generalization of geometry. Now, let me tell you this. We've been able to see that if y follow negative binomial, x is going to be y1 plus y2. For instance, take a look at this. If y1 follow geometric, y2 follow geometric, up to yr. If I sum all of them together, my x will follow negative binomial. Now, y1, let's say y1 actually means the numbers of Bernoulli trial before seeing the first success. Y2, the number of Bernoulli trial before seeing the second success after we have seen the first. Y3 will be the numbers of Bernoulli trial, okay, seeing the third success after we have seen the first and second. Does that make sense? Now, if I do this up to YR, okay, now the sum of this become, negative binomial. So in that regard, if I want to figure out what is going to be the expectation of x in the negative binomial, okay, now this is going to be having y1 plus that. We're using the knowledge of a linear combination here now, okay, and each of these, I'm actually going to have expected value of y1 plus expected value of y2, blah, 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 until I get to expected value of yr. And don't forget, then I'm actually going to be using the mean for this guy here. So which means each of that, I'm actually going to have 1 over p plus, so, the expected value of x here is 1 over p, right? The expected value of x here is 1 over p. So if I now want to derive the mean, okay, if I'm deriving the mean right now using the knowledge of linear combination. So expectation of s 1 over p plus 1 over p until I get to, and what would be the number? We say r, okay, 1 over p plus 1 over p in r time, okay, obviously going to be r over p. So expectation of s, okay, is going to be r over p. Well, now when r equal to 1, what does it become? When r equal to 1, the mean of a negative binomial becomes the mean of a geometric distribution. Now you can also, if you want to figure out the variance, of s, you're actually going to do the same. So the variance, but you know why we're actually assuming, y1 up to y2 are independent. They are independent. Okay, so here I'm actually going to have the variance of y1 plus the variance of y2 until I get to the variance of yr. And of course, what was the variance for geometric distribution is q over p squared. So I'm going to have q over p squared, in r time. Having a q over p squared in r time is just going to be rq over p squared. Okay, r q over p squared. So that would be the variance for the negative binomial distribution. So like I said, negative binomial distribution is a generalization of a geometrical distribution. So this guy, the negative binomial distribution is actually going to say, he's trying to figure out how many binomial trials are we going to have before seeing a good number of successes. That's exactly what that guy is talking about. Now, I want to go into another distribution, the discrete uniform. After the discrete uniform, I'm going to go to Poisson distribution. And of course, after that, that's what I'm going to have for you today. Of course, tomorrow, we're actually going to talk about another probability distribution from the discrete family that we call hypergeometric distribution. So if I were you, make sure you understand the connection of each of these distributions to real life. I just told you the essence in real life. We don't just do what we do. We got a reason why we do what we do. Okay, now I want to go into another distribution, very important in statistics. So we call that Poisson distribution. And I need you to pay attention. Please pay attention. You don't understand, ask question. Okay, make sure you ask question. You don't understand, ask question. Okay, now I want to welcome you to Poisson distribution. Poisson distribution, we use this distribution to model. We use it to model rare events. Event that occur in a blue moon. Like this is a very good distribution for rare occurrence. What is the probability? In a Minneapolis district, what is the probability that the accident will occur within 7 a.m. and 7:05? So what is the probability of having an event of earthquake? Those are rare events. So what is the probability of having event of a snake bite? So those are rare events. So if we really want to figure out, want to model or rare occurrence of rare event, then we talk about Poisson distribution. Now, how do we write this mathematically? We're going to say x follow poi with parameter lambda. Okay, parameter for Poisson is lambda, which is going to be the incidence rate, the incidence rate. So the probability mass function is actually exponential raised to power minus lambda raised to power x over x factorial, and start from 0, 1, 2 to infinity. Now let's take a look at what I have here. This is a probability mass function for Poisson distribution, exponential raised to power minus lambda raised to power x over x factorial. X here X here is the number of such occurrences. We could have 0, event of earthquake. We could have 1, we could have 2, and so on like that. Or maybe you want to talk about bank failure. Bank don't just fail. Okay, so if I want to model the incidence of bank failures, I'm actually going to use Poisson because it's a rare event. Or I want to model what is the probability that economy is going to go into recession. Economy don't just go into recession. Or what is the probability if a customer approach a bank for loan, what is the probability the customer is going to default or stuff like that? Now, this is Poisson distribution. Now, we can in Poisson distribution, we can actually derive the mean. The mean is lambda, the variance is also lambda, and the standard deviation of S is the square root of lambda. Don't forget, in the case of disease, okay, in the case of disease, the lambda there is just going to be the incidence or like a prevalence rate of that disease. Okay, now you know what I want to do right now? I want to show you how to derive this. And after showing you how to derive that, of course, I already have examples, the calculative examples in the lecture slide. Okay, so let me show you why do we care about the mean? Because we live in a world where we are interested in average, in a probabilistic world, where one of the basic statistical measure is average. Okay, this is like, oh, what is the average occurrence of such event? If we know lambda, then we know the average occurrence of such event. Then how do we actually measure the reliability of the average? That's why we need the variance and the standard deviation. Now I want to derive this, and I actually need you to pay attention to how this is going to be derived. Now, I want to find expected value of S, which is going to be summation X, probability of X equal to S for discrete random variable. My S is starting from 0 to infinity. Don't forget, every probability distribution has their support. Okay, you can see here, this is from 0 to infinity. Okay, so then I'm going to do S start from 0 to infinity S. What is that probability? The mass function is what I have here divided by X factorial. Now, what I'm going to do right now, okay, I can rewrite that S starts from 0. I have this exponential this, lambda raised to the power this, and this X factorial can be written as X into X minus 1 factorial. I can write that. I can write X factorial mathematically to be X into X minus 1 factorial. And of course, if that is what happened, this S is going to cancel that X. So if that S cancels that S, that I'm actually going to have S start from 0 to infinity, exponential is by this, lambda raised to the power X. I have X minus 1 factorial. Okay, so when I have that right now, this is what this is what is going to be the next. Now, what is going to be the next? Please pay attention. Okay, what is going to be the next is I'm summing from 0 to infinity. Then I'm going to bring this guy out. It's independent of X. So expectation of X equal this. Then summation S start from 0 to infinity. Lambda raised to the power X over X minus 1 factorial. Okay, now if this is what I have right now, lambda is carrying S. If I want lambda to also carry X minus 1, I can manipulate, okay? In my manipulation, I can bring in lambda and bring in lambda raised to the power minus 1. And this guy is going to come here, so I'm actually going to have this guy now, summation, then I'm going to have lambda combining this guy, and then I'm going to have this guy, then I'm also going to have this guy. Okay, now you can see lambda raised to the power that, and I have this guy. So if I let y be X minus 1, then it means I'm actually going to have summation lambda raised to the power y factorial, y start from 0 to infinity. Now I needed to pay attention to this in maths. According to Taylor or Maclaurin series in math, when I'm summing y from 0 to infinity, and something is carrying y, and we are dividing by the factorial of that in math. This guy means exponential raised to power lambda. Okay, so the whole of this guy is exponential raised to power lambda. So what do I have at the moment? What do I have? I have lambda exponential raised to power that, exponential raised to power that. That's what I have at the moment. And of course, this guy cancel that guy, right? Okay, because another way you can do, so lambda minus lambda, which is lambda exponential raised to power 0, which is going to be 1. So finally, you have derived the mean to be lambda. That's how we derive the expectation of S to be equal to lambda. Is there any question on that? Okay, so if there's no question on that, I'm actually going to move. How do you derive the variance? Okay, how do you derive if I'm too fast on the board, you can take a picture. Okay, you can take a picture. If you want to take a picture, that's no problem. Take the picture. Okay, but the most important thing is I actually need you to listen. Okay, you don't understand this question. Okay, now I've been able to derive the mean. Okay, I've been able to derive the mean. Okay, I now want to derive the variance. Okay, I want to derive the variance. Okay, so I've been able to derive the mean, that the mean is lambda. So right now, I want to derive the variance. So the variance of x is expectation of s squared minus expected value of s all squared. Okay, you know that? That's the formula. And right now, okay, don't forget, this guy, the other time I said it's the same thing as this. This guy, s squared. S squared is the same thing as this plus this. You know that? Okay. Now, minus this guy now. Okay. So right now, expectation into x minus 1. What is the e of x that we just derived? Lambda minus lambda squared, right? Then we need to work on this guy. Okay. Now, if I want to work on this guy, I need, what is the expectation of x into x minus 1 for discrete random variable? Is going to be s start from 0 to infinity. Okay, x into s minus 1, the probability of s equal to that. So right now, then I'm going to have s start from 0 to infinity, s into x minus 1 exponential by lambda, lambda raised to power x over x factorial. Okay, now what I did the other time, okay, so what I did the other time, okay, the other time I said x factorial, that is equal to s into s minus 1 factorial. So right now, I'm actually going to say s factorial equal s into x minus 1, s minus 2 factorial. Because it's going to keep going. Why do I project this to that? Because I want this thing to cancel out. I want s into s minus 1 to cancel out. So that is why I'm doing that. Okay, mathematically, without violating mathematical rule. Okay, so right now, I'm actually going to write expectation into x minus 1, okay, equal summation, s start from 0 to infinity, s into x minus 1, this lambda raised to power x, lambda raised to power x, this instead of x factorial. I'm actually going to have this guy. I'm actually going to have this guy. Oh my God, this guy canceled that guy, right? And if this guy canceled that guy, I'm going to bring this guy here, okay? Then I'm going to have this. And if I'm going to have that, I'm going to be left with s minus 2 factorial. And this is lambda s. So I can introduce lambda squared and lambda raised to power minus 2. The other time I introduced lambda and and lambda raised to the power minus 1. So right now, so I'm actually going to have lambda raised to the power x minus 2 divided by s minus 2 factorial, and the lambda squared is actually going to come here. You know, I manipulated introducing this guy, and this guy that can cancel out. Okay, why am I introducing this guy? Because since we have x minus 2 factorial in the denominator, in the numerator, you know, lambda should also carry s minus 2. So right now, okay, so now if I have this, if I let y to be x minus 2, so this guy is going to change into lambda squared, this guy summation y star from 0 to infinity, lambda raised to the power y over y factorial. And you remember what I said the other time about this. This is going to be exponential raised to the power lambda mathematically. And from here, you know, this is going to cancel this guy. And of course, this guy is just going to be lambda squared. So which means expected value of s into x minus 1 is actually going to be lambda squared. Okay. Now, what if I ask you to find this? Can somebody try, if I ask you to find this, x into x minus 1, x minus 2, you can find that. Expected value of s plus lambda, right? Expected value of s into s minus 1 was lambda squared. Then expected value of s into s minus 1, s minus 2 would be something. If you look at the trend, I'm not going to say it. Okay, now, right now, I want to come, right now, okay, I actually want to come back here. Right now, we've already gotten that to be lambda squared, right? We're going to plug that in. Lambda squared plus lambda minus lambda squared. What happened? So the variance of s is also lambda. So Poisson distribution has the same expression for the mean and the variance. Expected value of s is lambda. Expected value of the variance of s also lambda. Okay, now that is that. The calculation example is on the lecture slide. Now, I'm going to move to the last distribution because of my time. I'm going to move to the last distribution. Okay, the last distribution is a discrete uniform. Now, when do we use discrete uniform? For instance, I actually want to conduct a survey. And if I can conduct that survey in any day, okay, which means I can randomly select days within months, within 30 days. So discrete uniform means the probability of selecting that day is equal. That's equality. Okay, now discrete uniform. So discrete uniform is another probability distribution of a discrete random variable. Okay, the probability of x in discrete uniform is 1 over n. X start from 1, 2 to n. Okay, now we can write x follow discrete uniform. Whenever you see that, we're talking about discrete uniform. Now, how do we derive the expected value of x? Okay, you know, the expected value of x, I think it's n plus 1 over 2. The variance of x is 1 over 12 n squared minus 1. So how do we derive this? Yeah, I'm going to show you right now. So if I want to derive the expectation of x, this is a discrete uniform. So summation, okay, s start from 1 to n, x, probability of s equal to s. So which is going to be summation, s start from that to that, x 1 over n. Okay? X, what is the probability of that? 1 over n, because it's discrete uniform. If I have 1,000, the probability of choosing any one would be 1 over 1,000. That's why you see 1 over n for discrete uniform. But after 30 days, probability of choosing any one is 1 over 30. Okay, now, if I have this guy now, so it means expectation of x, this guy is a constant, 1 over n, summation x, s start from 1 to n. 1 over n, what is that? What is x? 1, so 1 plus 2 plus 3 until you get to n. In high school, you've come across sum of n numbers, sum of natural numbers. The sum of natural number as a formula is n into n plus 1 divided by 2. That is the sum of natural numbers. Okay, I'm going to do 1 over n into n plus 1 over 2. N cancel n. What do I have? N plus 1 divided by 2. So that is how to show the expected value of x for discrete uniform. Okay, now how do I show that? How do I show the variance? Please pay attention. Okay, so how do I'll show the variance for discrete uniform? Okay, so if I want to show the variance for discrete uniform, the variance of s is expectation of s squared minus expectation of s all squared. Of course, you know that. Right now, expectation of s squared, we don't know that. But expected value of x, we know that n plus 1 over 2 all squared that we just derived. Now we need to figure out this guy. If I want to figure out expectation of s squared, for discrete random variable, it's going to be summation, s start from 1 to n, okay, s squared, the probability of s equal to that. Okay, now, if that is what I have, okay, if that is what I have, so what I'm going to do right now, here, expectation of s squared equals summation s start from 1 to n, s squared, then what is the probability? 1 over n. Okay, 1 over n. And that's going to be 1 over n is a constant, s start from 1 to n, s squared. This is going to be, what is that? 1 squared, 2 squared, 3 squared, until you get to n squared, right? Until you get to n squared, right? Now, here I'm actually going to have that you need to remember the sum of squared of a natural number from math. The sum of square of a natural number is n into n plus 1, 2n plus 1 divided by 6. Has anybody seen this before? This is a formula for the sum of squared of natural number. So this guy is going to replace this. So right now, I'm actually going to have n into n plus 1, or 2n plus 1 divided by 6. And this cancel that. Then I'm going to have n into, I'm going to have n plus 1, okay, 2n plus 1 divided by 6. So right now, this is expected value of s squared. Now, if this is expected value of s squared, then what I'm going to do, I'm going to come back here and plug in that. I'm just going to simplify the algebraic expression. So now what I'm going to do right now, I've already gotten expected value of s squared. So this is going to be n plus 1, 2n plus 1 divided by 6 minus, this is going to be n plus 1 squared divided by 4. You see why you were doing this in high school? I know in high school, maybe algebra 2, you've done something like this. How do we simplify this guy? Now, to simplify, I believe you've noted this, right? You've noted this? Okay. Now, to simplify, I think I'm trying as much as possible to record this. And at times, the recording come out good. At times, it doesn't come out good. If this come out good, I'm actually going to publish that on my YouTube channel. Okay, now, what is the SCM? That would be 12, right? The SCM, so don't forget, the variance of S, so this is 12, okay? And if that is 12, 6 goes in 12, okay? 6 goes in 12, 2, okay? And here we're going to have n plus 1, 2n plus 1 minus 4 goes in 12, so 3 into n plus 1 squared, okay? Now, right now, what is common? Okay, n plus 1 is here. So if this is going to be 2 into 2n plus 1 minus 3 into n plus 1. divided by 12. Do you see that? N plus 1 is common. I bring it out. Okay, I bring it out. Okay, so right now, so I'm actually going to have n plus 1 into 4n plus 2 minus 3n minus 3 divided by 12. Okay, so here I'm actually having n plus 1. So here, 4n minus 3n, that's going to be n. 2 minus 3, that's going to be that, divided by 12. Okay, if you take a look at this guy, remember in maths, if I have a squared minus b squared, is a minus b and a plus b, right? So this guy, I can write that as n squared minus 1 divided by 12. And that is how we prove the variance of S to be equal to that for discrete uniform. Now, I've been able to handle most of the probability distribution of a discrete random variable. We've done Bernoulli, we've done binomial, we've done geometry, we've done negative binomial, and of course, we've done Poisson distribution, and of course, right now we're doing discrete uniform. Okay, for 1 minute, I'm quickly going to show you the calculation aspect. Calculation aspect is very, very crucial. So I will advise you get yourself familiar with how do I, wait a minute. 1 second. Let me see. Okay. Okay. Let me share that. Let me share that. Come on. Come on. Okay, it's gonna come up now. Now, I will advise that you go over. This is for Poisson distribution. How do we apply that in real life? Give you a scenario like that. You need to identify your lambda. You can find the probability of s equal to 0, s equal to 1. The moment you know your lambda, okay. At times, when they give you lambda in year, and they wanted to find lambda in months, okay, you have to recalculate your lambda. Okay, maybe initially they give lambda a year and they now wanted to find lambda in months. It's going to be, for instance, initially the lambda here is the one for the year, and they want to figure out the one for for the month, and you want to figure out the one for the year, you multiply by 12. Okay, if they say okay, the number of calls received in a day, okay, for a day will be lambda divided by 30 because you have 30 days in a day. So you have to get a good lambda to be able to understand what to do. So pay attention. The most important is how do I figure out my lambda? Okay, that is what is very, very important. How do I figure out my lambda? This guy said, if y represents the number of calls received in a year, number of calls received in a year, okay, and I want to figure out the lambda, you can see what I did here, okay? So in a day, lambda divided by 30, okay? It now depends. Now, if you take a look at this example, suppose that the number of snake bites seen at KKUA in a year, they say a year, has a distribution with average 6 bites. Lambda is 6. Lambda that is equal to 6 here is for a year, okay? Now, if they ask question that has to do with a year, you're actually going to be using lambda equal to 6 or 2. But if they change that from a year to a month, look at question 3. What is the probability that in a month? Or even if they say in 2 years, if in a year is 6, 2 years will be 2 times 6. And that would be 12. That was why you have 12 here. You can see lambda is 12 now because for 2 years. If for 1 year, lambda is 6. For 2 years, lambda will be 6 times 2. And in a month, lambda will be lambda divided by, they're going to be 6 divided by 12. Okay? Please pay attention to the use of lambda. And when next we meet, we're going to talk about the last distribution in a discrete family for this class, hypergeometric distribution. That is going to be the focus tomorrow. And all the materials for this week have already been uploaded. If I were you, before coming to class, why can't you go through the materials? So for 4101 student, you've already seen your result for midterm. 5101 student will see their results today. So check the canvas for the results. Is there any question before I go? Okay, be sure you all stay safe and have a lovely day. Happy new month. Oh, happy new month. Okay. Okay, bye for now, everyone.